my classes on fundamentals of electrical circuits, we move into the fifth section, which is AC circuits. Okay, and in session number 1, we'll be dealing with mostly easy problems in AC. Now, why is AC going to be easy for you? So certain rules have to be followed. That's all that we've got to do. Okay, so those rules will be counted as we go along through the different problems. Okay, so let's look at problem number 1. Okay, the diagram is more or less self-explanatory. Then we'll read the English part of it. You see here a source. Okay, so as we go along, please take care of some of the comments that I'm making. So Vt is given as sin t. It's an AC source because of the tilde shown in between. The magnitude is equal to 1. Okay, and that is the maximum value. So that please remember, when something is given as Vm sin omega t, Vm happens to be the magnitude, and whatever comes along with t, okay, especially before it, that becomes the frequency in radians per second, that is equal to omega. If on the other hand, something like Im sin omega t minus pi by 4, etc. are shown, then pi by 4 happens to be the angle by which the current lags the voltage. Okay, because it is minus pi by 4. On the other hand, if Im sin omega t or cos omega t, they happen to be the same so long as everything is in the same domain, either cosine or sine. Okay, so if Im cos omega t plus pi by 2 is shown, it means that the current is leading the voltage. Okay, because there's a reference. Okay, and the reference happens to be either the voltage or sin omega t or cos omega t. So what do we have here? V sin 1 sin 1t or omega equal to 1. There's no phase lag. There is a current flow through a 1 ohm resistor and an unknown impedance Z. Okay, and the result is perhaps what is shown. It's a sinusoidal picture, no doubt. Okay, the maximum values range between 1 by root 2 plus 1 by root 2 and minus 1 by root 2. And the zero current axis is shown, or the horizontal axis is shown, which is a time t, and there's a crossover. Okay, there's a crossover for the current, which it is shown, so it's current. Okay, so there's a crossover, zero crossover, which occurs at pi by 4, t equal to pi by 4. So much of information is given. Okay, now let's read the problem and then analyze it. Consider a circuit shown in the figure with input Vt equal to in volts. Sinusoidal steady state current It flowing through the circuit shown graphically when t is in seconds. The circuit element Z can be. Okay, so what all do we need to look at? Okay, first of course, as I said earlier, what is the waveform? Okay, so the waveform reveals many things. Like for instance, what is the maximum value? So the maximum value of the current is equal to 1 by root 2. And the maximum value of the voltage is equal to 1. So what's the impedance? 1 by root 2 or root 2. Okay, so this is how we proceed. Okay, another thing that's shown is the time. Okay, along which this waveform proceeds. Okay, the magnitude which was already spoken about, and that there is a delay. Okay, delay by pi by 4. So we see that we write it out as Im, which is 1 by root 2 sine. Okay, because the what is given is also sine. So sine omega t, where omega equal to 1, sine t minus pi by 4, because t minus pi by 4 has to be 0. Only then the magnitude will become equal to 0. Okay, because it's a 0 crossover point. Okay, which means that t equal to pi by 4. Okay, or in other words, when it is t minus pi by 4, it is lagging the voltage, which is equal to 1 sine t. So if it is lagging, the element has to be an inductor. So that's how we proceed. Okay, and since the total magnitude is equal to root 2, that is Vm, then V maximum, which is 1, Im, which is 1 by root 2. When you take the ratio, it's equal to root 2, which means that we have to have 1 plus 1, the 1 square plus 1 square, which is 2, and its square root. So definitely, obviously, omega L has to be, of course, we have already diagnosed that it is going to be an inductor, and so if the impedance of an inductor is omega L, and omega is equal to 1, so L is equal to 1. As simple as that. So of the answers, B is perfectly true. Okay. So some of the aspects that we need to remember is the waveform, that it gives the maximum value, and that voltage and current need to be expressed either in sine or cosine only. Okay, otherwise, okay, you have to convert them and such that you can compare them. Okay, so we have the magnitude, which is the maximum value. You also have a delay angle here. Okay, And from the circuit you picked up the omega value as also that there is a load Z. Okay, and then you also have the sinusoidal source as reference. Okay, and here we have a maximum value. In certain constants we will be given the RMS value. So let's make a distinction as we go along. Okay, and then current lags the voltage if inductive reactance, and leads the voltage if the reactance happens to be capacitive. So these are some of the points that I have collected together that we might be using. Okay. Let's go to problem number 2. The current in the RL circuit shown below. Okay, of course, there's a it's already given as 200. That's the source is given as 200 cos phi t volts. Okay, so 200 is the maximum value. It's not a sinusoid, but it's a cosine. Okay, so both if you are talking about a current, it should also be cosine. Otherwise, it has to convert it to cosine. Okay, and then omega is equal to 5. There is no so and the angle equal to 0. That is, it starts at t equal to 0. Okay, there's a resistor, there's an inductor. The current in the RL circuit shown below is IT equal to 10. Okay, so 200 by 10 will give you the impedance value, because when you look at RMS value, it will be 200 by root 2, and 10 will also have 10 by root 2. So whatever you can use maximum value or RMS value and take the ratio and get the impedance. So the impedance is equal to 200 by 10, which is equal to 20. So that's one part. Then we see that the current below is IT is equal to 10. Okay, so that we have already diagnosed. Cosine is given. So cosine means both are cosine. So we'll go as it is. Phi t, of course, it has to be phi t. Otherwise, there will be harmonics. You will not be able to calculate. And then minus pi by 4. So the current is lagging the voltage. Because both are cosine, you can say directly that the current is lagging the voltage. So it's an inductor. And the picture gives us an inductor. Okay, the value of the inductor rounded off to 2 decimals. So what else do we diagnose from pi by 4? We say that we realize that both R and the omega, that is the reactance, should be equal. Only in that case you get the an angle equal to pi by 4 because of the horizontal, the vertical size of the impedance triangle divided by the and the horizontal part will give you the resistive element. So if they are both equal, only then you are going to have the impedance as at the diagonal as root 2 times R or root 2 times omega L. Okay, so omega L happens to be the vertical portion, R happens to be the horizontal portion of the impedance triangle, and since they are equal, or they have to be equal because the angle between them will have to be pi by 4, and the impedance will be root 2 times the resistance, or resistance divided by root 2, or omega L divided by root 2 will give you the impedance. Okay, so now we have the impedance already with us, because 200 by 10 is equal to Z. So omega L will be given by just simply dividing it by root 2. Okay, so once you have that value, then that gives you gives you omega L. So simply divide by omega, which is equal to 5, and you get 2.83 Henry as the inductive the value of the inductance. Okay, so moving on to problem 3, we have a 16 angle 0. Okay, here we come to an RMS value being given. Okay, so both aspects that we have been mentioning is here there, except for the fact that omega is not mentioned. Okay, and what is given is the RMS value. So 16 is the RMS value, and the phase angle lead or lag is equal to 0. So there's no neither lead nor lag. So this is the reference. There's a current source, and then it is met by a network of impedances, 25 ohms, J30 ohms, minus J50 ohms, and 15 ohms. Okay, and what is asked is, in the circuit shown below, the Norton's equivalent current in amperes with respect to the terminals PQ. So you just short PQ and Q and try to obtain the current flow through it. Okay, once you short it out, minus J500, which is the impedance of which is the reactance of the capacitance, becomes bypassed. Okay, so now we have 25 ohms in parallel to 115 plus J30. Okay, so that's very easy to solve it out. Okay, so we have 25 parallel with 15 plus J30. So that's it. Okay, and then we also see that the current that is flowing through the short is also the current that is flowing through 15 and J30. So you don't have to parallel. You simply have to say that 16 into, you have to use the current division rule. So 16 into the other impedance, which is 25, divided by 25 plus 15 plus J36. So we see that we have on the denominator, that is 16 into 25 divided by 40 plus J30. We see that the same combination of 4 and 3 have come. Okay. So if 4 and 3 have come, or 40 and 30 have come, then the total is then the impedance value is going to be 50. Okay, if 6 and 8 are there, then the impedance value is going to be 10, or 60 and 80 will give you an impedance value equal to 100. Okay. Moreover, the angle is, as we mentioned before, since it is J30, it is going to be 36.9. Okay. But of course, we don't have to go for that at all. We just have to find out that this is giving rise to a division of current into the rectangular and the rectangular coordinates, where we see that the current is equal to 16 divided by 25 into 5, that is 25, that's you have 16 to 25 divided by 50, because 40 and 30 will give you 50, which is equal to 8 ampere. Okay, and then it is going to divide into two. Okay, one is the rectangular, one is the horizontal component, the other is the vertical component. So what is the horizontal component? Horizontal component is larger, because 40 plus J30 is the way it has been divided. So it's going to be 0.8, and the other quantity is going to be 0.6. Okay, so these things you can carry to any exam hall and do it directly. That's the reason why now we are having, and 40 plus J30 is on the denominator, so the angle is going to be negative, or in other words, you are going to have a minus in between. Okay, so since we are going to repeat such problems again, I'm not going to repeat the whole thing again, but I hope you have understood that the way that the mind can work without using a paper or pen is that 16 into 25 divided by 50 angle 36.6. Okay, so we see that it's 8, and there's a negative angle on the numerator. Okay, if there's a negative on the angle numerator and it's equal to 36.6, then you are going to have the horizontal component as equal to 0.8 and the vertical component as equal to 0.6 with the minus, the sign is going to be negative because of this angle being negative, so it's going to minus j 0.6. On the other hand, if it had been 30 plus 40j, then again the value will be equal to 50. That is, the impedance value will be equal to 50, but the angle would have been 56. Okay, it would have been 56.1. Okay, and then when it comes to the numerator, it will become minus 56.1. Okay, and it's the division into 2. That is, one angle so much is the same as equal to or 8 into 1. Okay, so 1 is chosen as the magnitude, and then it would have been 0.6 minus, because of the angle, negative angle, minus j 0.8. Okay, so I suppose this will be remembered. So now it's very simple. 8 into 0.8, 6.4. There's one answer only, and with 6.4, so you go directly for it. Okay, so you can also see that 8 into 0.6 is equal to 4.8, and the negative has to be reflected in the answer as well. So A is the answer. Moving on to problem number 4, we see that here we are having two current sources, one going downward, the other going upward, and the difference between them is going to move upward through the 3 ohm resistor. We also have an inductor and a capacitor. It's a fully AC circuit because the current source on the left is phi angle 0. Phi is the RMS value and 0 is the phase lag, which is 0. And the other current on the rightmost end, which is flowing downward, now has a RMS value. Okay, I am repeating this again and again. It has an RMS value is given by 10, and there is an angle of lead equal to 60 degrees. Okay, so it has two components. Okay, as we very well know, the two components happen to be, because cosine 60 is the horizontal component, which will be equal to 0.5. Okay, and sine 60 plus j. Okay, because it is a positive angle, plus j, sine 60 will be root 3 by 2. So 10 into 0.5, that is 5, plus j 10 into root 3 by 2. So that's the current that's coming down. Okay, and what are we supposed to find out? For the circuit in phase, the current is. Okay, as we guessed. Okay, so now of this current, one flows off. Okay, what is that? Phi angle 0, or phi is robot. Okay, so we already had 5 plus j 10 into root 3 by 2, of which 5 is removed. Okay, and the rest flows through the resistor 3 ohm, and that's equal to 10 into root 3 by 2 with an angle j. Okay, or angle 90 degrees. Okay, j is equal to an angle 90 degrees. Okay, so it's a very interesting problem. You can even develop it further to see whether the current source, which of the current source is delivering, which of the current sources taking power, etc., by trying to find out the voltage. Okay, so everything becomes clear once you find out the current, and you can analyze it further if required. Okay, moving on to another indicative problem, which is fifth one, where we are having a current source phi angle 30, RMS value 5, and an angle of lead equal to 30 degrees. Okay, this current now has an opportunity to flow through two impedances. Okay, both are intimately connected with respect to each other, because one is 5 minus 3j, the other is 5 plus j3. Okay, So if it is 5, so if we are having A plus JB and A minus JB parallel together, let's learn forever what is going to be the result. Okay, so you are going to have, okay, because you are going to remove the we are going to try to, okay, of course the J component gets removed. Okay, so since we are, so we will be multiplying and dividing both by the same, by the conjugate, etc. Okay, so don't go for all that in the exam context. Just remember that if A plus JB and A minus JB are in parallel, then the result is going to be A square plus B square divided by 2A. Okay, the first quantity. Okay, so 2A, which is the real component. Okay, so that's, so in this case you are seeing that it's going to be 5 square 25, and then you are going to have 3 square, which is 9. So 25 plus 9, 34, divided by the real component, which is 5 multiplied by 2. Okay, so you're going to have divided by 10. So yeah, divided by 10. So the 25%, 3 points. Okay, so do we require this working? Let's see. In the network shown in the figure, the phasor voltage VAB. So we need to find out the total voltage. Okay, so now this current 5 angle 30 multiplied by what we got right now. So you're going to have an angle 30, because this the impedance value is going to be fully real. Okay, so we have the, okay, so now we see that 5 angle 30 multiplied by 3.4, which is equal to, as mentioned before, angle 30, and 5 into 3.4, 17. Okay, so answer D is coming right. Okay, and this concept, okay, so we are collecting concepts. We hope that it will be useful for you in the next problem also. So I have placed them together, more or less together, such that we have a revision. Okay, in problem 6, we again notice that similar to 5 angle 30, this time we are having 14 angle 0. So that so here we have voltage source for one thing, and moreover it can be the reference, because the angle is 0. There is neither an angle of lead nor lag. Okay, and it is connected to a star delta kind of circuit. J4 on one side, minus J4 on the other side, supported by 6 ohms at the middle, and then again both legs have 6 ohms. Okay, so this is not a Wheatstone bridge. Okay, because if you take the ratio, J4 by J6 is not equal to minus J4 by 6. Okay, so 6 matters. Okay, so the 6 ohm connected between them matters. Moreover, we are having a delta circuit here. This is very important, because once you resolve the delta into a star, then you have the same old situation wherein you are having A plus JB and A minus JB connected together in parallel. Okay, so the resolution of the delta into the star is shown, because they all have equal values. The star will have 1/3 the value of the resistors, as was mentioned before. It's all 2 ohms. Okay, so what do we have on 2 legs parallel together? They are J4 plus 2 and minus J4 plus 2, or 2 plus J4 and 2 minus J4. Okay, so what's going to be the result? We see that it's equal to 2 square, that is 4, and then you are going to have 4 for the 16 for 20 divided by 4. Okay, so it is 5. Okay, and moreover there is another resistor in series with it, which is the 2 ohm resistor, which forms the bottom part of the star. So we have 5 and 2, 7, as is expected, because 14 was given as the voltage. So we see that this voltage is now across a purely resistive circuit, which is equal to 7 ohms. Okay, 5 plus 2, 7 ohms. And what is asked of us is to find out the current I, which is the current that emerges from the 14 angle 0 volt source. So it is as simple as 14 divided by 7. So it is 2 angle 0. Okay, so it's a simple problem, but then it is more or less a repeat, but there are differences. Like for instance, in the earlier case it was current source. In this case it's a voltage source. We also had a delta, which we had to solve into a star, such that the rule that A plus JB parallel to A minus JB can be equated to A square plus B square by 2A, where A happens to be the real portion. Okay, so it becomes purely resistive. The whole thing becomes purely resistive. So moving on to problem number 7, which is also an easy problem in AC, where we see that there is a 100 volt source, and we have 80 volt across the resistor, 40 volt across a reactance, inductive reactance. So it is actually equal to something with J there, and then we also have okay, or in other words, they are not along the same line, okay. And we also have a capacitive, which again has a voltage across it, but then this voltage and the voltage across the inductor are going to be oppositely directed, so the difference has to be taken into consideration, and then 80 square plus that voltage square will give you 100, okay. So obviously it has to be 60, okay. So let's see, it has to be 60, the total has to be 60, okay. And because this is a vectorial addition means that you have to use the voltage triangle, which is a follow up on the current triangle, as also on the impedance triangle, okay. So what is asked is the the voltage VC across the capacitor. So obviously we need to get a value equal to 60, okay, from the difference between the two. So we are from the difference between the two voltages, one across the inductor, the other across the capacitor, okay. So it has to be 100, such that 100 minus 40 is equal to 60, and then 60 square plus 80 square is going to be 100 square, or the result is going to be 100 volt, as is shown by the voltage across them, okay. So the same concept is again now continued but in the current case here, and that's problem number 8. We see many ammeters, A1, A2, and the ammeter A1 measures the current through the resistor, A2 measures the current through the capacitor, and A3 measures the current through the combination, wherein a voltage source has been given, which has a magnitude 100, okay, right. Okay, in these two cases we are given a magnitude, okay, 100 and sine, okay. So the 100 volt is not, okay. So the 7th problem, I'm sorry, I did not mention it earlier. This is an RMS value. It is not mentioned as 100 sine omega t. So what is given is RMS value. That's why we are squaring 80 square and 60 square, okay. Of course, even if it's the maximum value, it happens to be the same thing, but then you can take it as an RMS value unless the sine or cosine component is mentioned, okay. So here we are having 100 sine omega t, which is the maximum value, okay. And what is asked of us is that in the figure A1, A2 and A3 are ideal ammeters, so everything measures everything ideally, okay. If A1 reads 5 ampere, so what does A1 measure? It measures the current through a resistor, okay. And A1 reads 5 ampere, A2 reads 12 ampere. What does it mean? A2 is reading a current which is opposite, which is at orthogonal or at 90 degrees with respect to the current flowing through the resistor. So we can see that that's going to be 12 square, okay. So 12 square plus 5 square, that is 144 plus 25 is 169, and its square root is what is going to be the current that A3 is measuring, and that is exactly what is asked. Then A3 should be, which is 169, when you take the square root, is going to be equal to 13 amps, okay. So 13 amps, okay, as simple as that. That is option number 169 has a root equal to 13, okay. So moving on to 9, I am covering more problems in AC because more problems are coming, okay, in gate examination, okay. Of course, my reference is always gate examination, though I am talking about fundamentals of electrical circuits, okay. So moving on to problem number 9. Here we are having a input and output shown for a circuit element, wherein we are having 1 kilo ohm and 10 microfarad, okay. And what is given is that in the given circuit, the steady state voltage output corresponding to the input. So input is shown as 3 plus 4 sine 100t. So what happens to 3? Okay, so so of course 3 is referring to a situation wherein it's okay. So now we are applying superposition. Okay, so what does superposition tell us? Superposition tells us that we are having we can consider the input voltage separately, 3 separately from 4 sine 100t. So what does 3 do? When 3 is applied, the capacitor becomes an open circuit. So whatever voltage is there becomes completely available at the output. Whatever voltage is applied at the input becomes completely. So 3 is there as it is. So of the 4 answers, A, B and D are correct with respect to the DC component. Now let's come to the AC component. What happens when we apply 4 sine 100t? Of course, the capacitor now becomes an impedance, and the impedance is the same as equal to 1 by omega c. So it is, so what is the omega component? That is 100. Okay, so 1 by 110 microfarad. Okay, so we have 110 microfarad, and then we have a potential divide. Okay, so so that's equal to 10 raised to 6 divided by 1000 or 1 kilo. So 1 kilo happens to be the both the voltages, both the impedances. One is a resistive component, the other is going to be a capacitive reactance. Okay, so again, when you take the impedance, they have to be squared and added. So if you are taking the total, you have to total it with respect to their vectorial inputs, vectorial content. So we have root 2 coming there. Okay, so we are going to see that the input is 4 magnitude, and so if you are going to add sign, we'll add sign. Okay, so it is going to be 4 by root 2, and sign is okay. And now what about the angle? Okay, so now when you're giving an input as equal to sine 4 sine 100t with no angle of lead or lag, the capacitor now will give rise to a current flow through it. Okay, and thereafter a voltage drop across the. Okay, so this was the current. So now it's going to have what is called as the voltage is asked. So the current is of course from a leading reference, but the voltage that develops across the capacitor now has to lag the current, because current is leading, or in other words, it's the same as equal to obtaining an angle as equal to minus pi by 4. Why pi by 4? Because both the resistance and the capacitive reactance are of the same value of 1 kilo. Okay, so now we have a totality of voltage available across the output as given by 3 plus 4 by root 2. Okay, because we are using sine, we need not find out the RMS value, so it's going to be 4 by root 2 sine the same old 100t minus pi by 4 volts. Okay, on the other hand, current was there, it would have been leading. Okay, so the current that is drawn from the voltage from the input is going to be leading, but the voltage that is developed across the capacitor is going to be lagging the current. Okay, so these aspects, they are a little tricky, but at the same time, if you imbibe them now itself, all AC problems are going to be easy. Okay, so the same concept again is repeated in the next problem. Looks like that because we again have 100 cos 3t. Okay, so earlier it was 3 plus, so there was a DC component. Here there's no DC component. Okay, so as we compare, let's hope that you learn better. Okay, so then it was 4 sine 100t, where 4 was the maximum value. Now here is 100 is the maximum value, and cos is going to be the cosine. The waveform has a cosine content, unlike in the earlier case. Okay, and the omega was 100 there. In this case, we are going to have omega is equal to 3. Okay, and what happens is that we are having 4 ohms and 1 Henry as the reactance in the series circuit, and the shunt circuit is going to have 5 ohms and 1 by 36 farad. Okay, so 3 is going to be utilized to obtain omega L as also 1 by omega C. Okay, and 2 voltages are shown, V1 and V2. Okay, so how do we proceed? The figure shows an RLC circuit excited by the sinusoidal voltage 100 cos 3t, where t is in seconds. The ratio of amplitude of, just like earlier, the ratio of amplitude of V2 with respect to V1. Okay, so now this 100 cos 3t is going to be divided between the two impedances. The first impedance is going to be 4 plus omega L. So 4 plus 3j, because it is inductive, so 3j, positive j, which is equal to 5 angle. Okay, 5. I hope you remember the magnitude is going to be 5. Okay, and there is also going to be an angle there. Okay, and when you look at the next circuit, that's going to be again 5 ohms, and then we are having what is called as 1 by 36. So 1 by 36, when you use omega, it's going to be 1 by omega and omega into 1 by c. So 36 by 3, that's equal to 12. And so as we got in the early case, 12 square plus 5 square, that's equal to 169, and the square root is going to be 13. Okay, so we are having 13 here. And okay, in the upper arm we are going to have 5. Okay, so we are going to have 5. So now we can divide the whole 100 volts by the total impedance. Okay, and then okay, so now you can add up all the impedance and you can divide the whole impedance, and then you can have and you can have a ratio. Okay, you can have a ratio by dividing the impedances. That's right now enough. Okay, so we have V2 is proportional to as we saw earlier 13, and V1 is proportional to 5. So 13 by 5, 2.6 is going to be the ratio across the voltage dividers formed by two separate impedance branches. One is the series element, which is having 4 plus j 3, and the other is going to be 5 plus j 12. Okay, so now we have taken the impedance directly, so every angle has been taken to consideration, so we don't have a problem. Okay, so we just take the voltage division as the impedance division. Okay, so let's move on to the 11th problem. So what do we have here? Again, it looks like very similar. In circuit, okay, so we have 100 cos omega t, so omega is not shown, and then we are having voltage V2 across 1 ohm and 1 Henry, and we are having V1 across 1 ohm. Okay, so that's it. And in the circuit shown, the positive angular frequency omega in radians per second, at which magnitude of the phase difference between the voltage and V1 and V2 equals pi by 4. Okay, so now the inductor has to create a voltage difference when compared to the two when compared to the rest. Okay, so now we need to have what is called as a phase difference between the two. Okay, so the phase of V1 is going to be the reference, because only a resistor element is there, but on the other hand we have to create an angle of lag. Okay, we have to create an angle difference of pi by 4, because but it's an inductor, so it will create an angle of lag for the current. Okay, because the voltage is given as 100 cos omega t. Okay, and that will give you, okay, so we need to have 1 square, which is the resistive impedance, plus omega, we don't know that, so we say omega into 1, this, because inductance is equal to omega square. Okay, omega square, 1 square, omega square. So 1 plus omega square should be such that you are having what is called as an angle of you should have it as equal to root 2. Okay, so only in that case you can say that there is an angle of pi by 4. Okay, so I suppose it's very clear that the frequency is the same as equal to omega equal to 1. Why? Because now we need to have the resistance value being equated to the reactance value. So omega equal to 1. Okay, a very simple problem. Only the concept of this concept has been excavated several times in gate examination. See, so let's come to the last question in this session, which is actually comprising of simpler problems. So it's the 12th problem. What do we have there? Just as before, we have a voltage source, an AC source marked as V in, that's the magnitude perhaps, and R and L connected together. Okay, and we read the problem as the RL circuit of figure is fed from a constant magnitude. Remember, the magnitude is going to be constant. Okay, variable frequencies are inside the voltage source. Okay, so the magnitude is equal to Vn. Okay, but the frequency continues to change. Okay, at 100 Hertz, the R and L elements each have a voltage drop equal to URMS. Okay, so what's special about the voltage drops across R and L happen to be that their squares, they are vector. You get the total voltage as a vectorial addition of both. Okay, so it's going to be URMS square plus URMS square is going to, and the square root will give you what is called as the total voltage, or V in is equal to root 2 URMS. So suppose that's clear, and a diagram is given to explain this. Okay, if the frequency of the source is changed to 50 Hertz, so what is going to happen? Let's see the new voltage drop across R. Okay, so R is the resistance. Okay, and now omega L has changed from omega L to, it has changed from 100 Hertz, omega corresponding to 100 has now become equal to 50 Hertz. Okay, so now omega L becomes the same as equal to omega L by 2. And what was omega L? It was the same as equal to R earlier. Why? Because they shared the same voltage. Okay, so now it is so now the resistance or the impedance pattern is such that we are having resistance R for resistor, which has not changed, and that omega L has now become, instead of R, it has become R by 2. Okay, so and across this we are applying the voltage, the same old voltage, the magnitude is the same, which is equal to root 2 URMS. What does it mean? That is, the current through the voltage across R will be the same as equal to the total voltage divided by the total impedance multiplied by R. So what's the total voltage? Root 2 URMS, okay, which is not changed, divided by what is the resistance? What is the impedance total? It's square root of R square plus R by 2 whole square. Okay, which is 5 by 4 R square. Or if you take out the R from outside, if you take out the R, it becomes root 5 by 4. It becomes root 5 by 4. Okay, and then multiply this current by R to get the voltage across and the resistance R. So this both the R's cancel, and you have root 5 on the denominator, and root 4 goes up as root 4 into root 2 is equal to root 8. In that sense, answer C is correct. Okay, so we have been examining the easiest concepts, but at the same time, the oft repeated mistake happens to be that when you're adding quantities, okay, when you're adding voltages, etc., which are in series, remember that in AC you always have to go for the vectorial addition. Okay, so the reactance components need to be separated from the resistive components, and the squares need to be taken of both, and then you have to add them, and then the resultant has to be taken care of. So this has been the pattern in almost all problems in this section. If you recall the problems, and if you go back, you will see that we have been dealing with the easy concepts with this particular refrain or warning that you had better be careful about. Okay, so thank you.